Hi, this is Robin Beaumont here in one of a series of videos introducing SEM, Structural Equation Modelling. We've been working through a set of examples that you can find on this web page of mine, and we're now up to comparing groups using a Holtzheimer and Swinberg dataset. Remember, you need to have downloaded some software. Actually 3 bits of software, all listed there. Let's just look at a little more of the details of what we're going to do in this session. So as I said, we're going to carry out a multi-group analysis using Onyx, which produces SEM diagrams and also source code for various R packages. We've used the Holtzheimer and Swinberg dataset before. It actually had 2 schools in it. We're only going to be concerned this time with one school, the Grant White school, but we are going to be looking at both boys and girls data for 6 particular tests. He actually did 26 tests, but we're only going to be looking at 6. We hypothesized and proved that there were 2 underlying factors, and those underlying factors we called visual perception and reading ability. And now we're going to be looking more in depth at the boys and the girls. Previously we only looked at the girls data, if you remember, in the dataset there, the rgmt_fem.dat. In that previous screenshot of the website, you'll notice there's also an rgmt_mal.dat, female data that you need to download as well. So the question is our factor analysis model different for boys and girls? Now the question is, what do I mean by different? It's alright if you've got a very simple kind of experiment where you're talking about means and the difference between the 2 means in the groups. Well, here we're talking more about differences to do with 2 aspects of the model. The first aspect of the model was to do with the measurement side of it. And if you remember, the measurement side of an SEM model is the arrows from the latent variable to each indicator. And so what we're saying there now is, do the factor loadings differ between the males and the females? So we were comparing the factor loadings between the males and the females. Interestingly, when you take this approach, you don't constrain the residual variances, you just constrain the factor paths. Secondly, there's a structural side to the model, that is the latent variables, how they relate to one another. And we've only got 2 latent variables, remember, in this model, and they have a correlation, a covariance. The question is, does that covariance differ between the males and the females? So again, we compare the 2. The data we're going to be using, as I say, is in 2 files, the grnt_fem.dat and the grnt_mal.dat. Also in units, we could have actually used another file I've got on the previous page of the website, which actually has all the data in one file with a gender grouping variable, where male is 2 and female is 1. I think you have to have the grouping variable actually in grouping variable order, if you know what I mean. I'll just show you that. So I'm very clear. Here we have the complete data set, which we're not going to be working with initially, where we have gender, which is 1s, and then we go further down, there's a load of 2s. Originally this data file had 1s and 2 rows muddled up. I don't think Onyx works when the indicator variables are muddled up. I'm not quite sure about that, but I did get strange results when I did it initially with that approach. Back to the aims for the session. We're going to be demonstrating how to use multiple data files, that is the data file with the males and the data file with the females. I'll also show you quickly how you can use the grouping variable, but I'll concentrate on the 2 separate files at the moment. And I'm saying we'll be looking at the parameters and how we can set parameters to be the same across 2 different samples, 2 different groups, the males and females, and we'll demonstrate the process of testing that across groups as well. Finally, a little thing in Onyx called iconification, which we'll be looking at, which actually makes it easier to compare several models on the screen. Let's begin. So first of all, we need to start up Onyx, which, if you remember, we downloaded and saved into our local drive. I'm just going to show you there. It's at the moment called Onyx-1.0-953. Probably most of the time when you were watching these videos, it'll have upgraded since then, and we downloaded that from the website. And if you double click on that, the Onyx window opens. There we are. Get rid of tip for the day. And what I'm going to do now is load the model we had from the contrariety factor analysis plus that data set of females. So here's our previous model with the females, and we need to actually restore the links between the data. So send data to model. So we opened it up again, and you can see there that they've now got a thicker border around them, indicating that they're linked to the data. And also if you move up and down, you can see data window moves up and down as well. I'm just checking that we've got the same values as before on another page. Yep, we have. Remember, we set both of these variances to the residual variances, latent variance to 1, so that's an equivalent to a correlation, that covariance value there. So we've done all that before. Now we've got to do is create another model of males and then compare the two. So what we do, being as we know we're going to be comparing exactly the same structure of the model, that is the same indicators and same latent variables, we first of all get the data from our males. Here's our data for the males, grnt_aml.dat. Just put that on to the canvas, close the window, and now we have two data files. And so we've got to copy this model and link it to the male data file. So to copy the model, we select it all, that's left mouse click, hold down and drag. Then once we're in a particular object, that's quite important, you have to be in a particular object, right mouse click, I forgot which my left and right was there, and then we go edit, copy, edit, copy, and then we go again, right mouse click outside this time, edit, paste. And notice when I did that it said paste and rename. If you'll notice here that that's exactly the same, and it's got the same values as the previous model, so it thinks it's just a duplicate, which we don't want. So what we're going to do is actually rename it manually ourselves. So I'm going to rename each of the error variances. We put an E, an M in front of each of the E's. So click on one where it says E1, we just call it ME1. Similarly here, I'm just going to call this BB. Similarly, I'm going to go through the whole thing and do that. I'll see you in a minute when we've created our model with the new names. So here we are with our two models, one for the females on the left and one for the males on the right. Notice what I've done is added an M to all the error variances, added an M to the actual names, which we didn't need to do, and added an M to each of the paths, the regression paths. And also I've added an M to the covariance, the correlation between the two latent variables. So we just need to link those to our male data set. Perhaps that's why I shouldn't have bothered renaming them, because it's written over the names I'm dragging. So if you're going to rename them after you've linked the data. I just find it's easier if you're looking at the results in the results window to have them named as such. So I'll just do that quickly now. And I'll carry on like that till I've done all 6. So here we are back now with our two completed models, and I've just moved the dataset over a little bit so you can see we've got the female dataset on the left, male dataset on the right, and if we click on each of these we can see that the dataset moves accordingly. So now this model is allowing us to create a parameter for either the males or the females. It's not constraining any of the parameters to be equal between them. The important thing to do before we start adding constraints to parameters is to make sure we save this model. And I've saved this model as Holtzinger underscore Swineford underscore GW underscore both underscore gender underscore M1. So we've saved that model, and now I'm going to open my next model where I've copied this model and just changed some of the parameters to be constrained, as we'll see. Go to File, Load Model or Data, and what we have here is an example there where it says constrained. And we can see this model now. You can see what I've done here is I've called each of these paths. It's easier if I click on one and show you. I call that VV, and it's the same VV there. And I've done the same. They were actually the first letter of each of the original variables. So it's VL for lozenges. Here it's RP. Here RS and RW. So now we have a set of parameters which are totally constrained, and you can see they're identical between males and females. Notice I haven't constrained yet the covariance, the correlation between the two latent variables. So now we want to compare these two models to see if there is any actual difference. And the easiest way to do that is to click on here and then drag our link. If you remember, we had a link, a little line between the two, but the screen's getting rather cluttered, so what we can do here, right at the bottom it says iconify. So you click on there, iconify, and it automatically adds a link between them. You can see. If you hover over it, we should get a result, but we don't. We get a warning saying model estimates for at least one of the models are not available. That's because we just opened up another model and we haven't linked our data to it, so we need to do that, and then it will work fine, which I'll do and I'll show you in a second. So now we've tidied up our constrained model. You can see I've added the standardized estimates as well, and I've when I joined it to the data set, the male data set, I added the M's in afterwards. We'll see why in a second. Let's go now to our comparator bubble, and we see now we have a -2 log likelihood and a p-value of 0.6. So that's saying there's no difference between our more constrained model and the model where we had different parameter values for each males and females. So we can use the same model for both males and females in terms of factor loading scores. The question is, can we do the same for the relationship, the covariance between the two latent variables? And again, we do exactly the same. Click on there, and we will change it to a name, whichever it can be, CV, as long as we choose the same name here. CV. There we go. And now do the same. I'll just click off there, and we can go here again. We should really leave it a little while to run to get itself organized. And we see now we have 0.583, p-value of 0.583, so it's still not significant. So there's still no difference between our model with no constraints and a model where we've constrained the male and female paths to be equal, and also the covariance value between the two latent variables. Obviously we could have actually compared the two by looking at the summary statistics for each. So if we click on our iconograph model, double click on it, left mouse click, we get model appearing again, and we can go show estimation summary, and that is for that model. Then we can do exactly the same for this model. Clear show estimation summary. Okay, another set of results. We can save these sets of results easy enough to a text file and compare. Now perhaps you'll see why I was so keen on renaming the variables, because you can't tell which are the best spec for males or which are the best spec for females unless you put an M in front of them for the male values. And we can go down and we'll get a set of fit indices as well, which we could have actually taken the two chi-squares, compared the two with the different degrees of freedom, and we've ended up with the same p-value as we got there by dragging. Obviously you could change other parameters or change some sets of parameters and compare with the previous model, and it's a nice way of investigating a set of data. Let's just go back to what we set out to do at the beginning of the session quickly. Have we completed these aims that I set out to? We've demonstrated the use of multiple data files. We will in a sec look at using a grouping variable and how that works. We've set parameters to be equivalent so we can compare groups of data, that is the males and females. We've demonstrated the process of testing a CFA model across groups as well by doing that, and I've demonstrated the iconification process. Let's have a look now at how we could have actually used a grouping variable instead. Here I've opened up the original model we had with our females, but I saved as a different name. Now we can see grnt underscore gender underscore subgrouping, and I've also used a different data set here, you'll notice, and there's a new variable there called gender, and that's basically just a grouping variable which goes from 1 to 2. We link these as usual to the data set, data to model. I use slightly different names, so it can't link them if it hasn't got exactly the same name. Now, what we've got to do is say we only want to use the males or the females, and remember that the males are coded as 2 and the females are coded as 1, so we've got to add what's known as a grouping variable. So we select all those by left mouse clicking and dragging, and then when we're in one of the variables, right mouse click, and it said add grouping. Add grouping there, we're still selected, and we say add grouping of gender, and we just make sure we drag that gender variable right onto the diamond. The diamond goes dark, which means it's using it, and it's basically just using the rows where gender equals 1. So that's a set of values for gender equals 1. We'll just carry out the same process as we did before, if you remember. Select it, copy, and then create another model at the side of it, but that time we would change that to 2. So we would select all the 2s, and we could carry out the same process we did with one data file instead of using 2 data files, and we get exactly the same results as before. I won't bother to show you that because I'm sure you can work out how to do it from the other demonstrations I've given previously. Just before we go, I would like to give some additional information. I've made it seem like a very easy, quick process. It isn't at all, and we'll just talk about a few aspects that perhaps we should have considered, but we didn't. So let's look at these issues that I want to bring up quickly. Well, first of all, we can actually compare individual parameters There's two ways of doing that. The first way is what's known as the Lagrange multiplier test, the LM test for short, and that basically tells us how much better the model would fit by using chi-square values and looking at how much they're reduced if a particular fixed parameter were allowed to be estimated. So in my mind that's equivalent to possibility of adding paths, adding estimated paths. In the other direction we can look at another approach called the wall tests, but before we mention that, it's actually quite easy to carry out Lagrange multiplier tests in Onyx by exporting the model script, which you can do just by clicking on one of the pop-up menus and it says export script, into the Lagrange R package, and then you just use one line of code which is modification indices with the name of the model that you created before, and that produces your Lagrange statistics for you. As I say, this other approach, the WOLD tests, called the backward search test, indicates which estimated parameters can be dropped without affecting the model. So that's the other way around, that's thinking about which paths you can actually drop, because remember, if there's not a path between two variables, it's equivalent to the correlation equal to 0. Other software packages, commercial packages such as AIM or what have you, allow you to look at all possible configurations of your data, but there's a huge problem with combinatorial explosion. In other words, you get a ridiculously large number of possible models, and of course most of them don't make any sense at all. So it's relying upon your expert knowledge in the field to make sense of these models, and some of these models can be equivalent. Just because they look different, they might not be any different underneath when you look at the matrix. Remember, SEM basically compares this matrix S that you provide it, the matrix covariances. Remember, we used that as an example in one of the previous examples where we didn't use raw data, and then compares this with something it creates called capital sigma, which is from the model we design, and it attempts to minimize the difference between those two. Also, when you're looking at parts of the model, you can think about residual analysis. You can look at how much a difference is between particular areas of the model. If you think about it, it's like putting a new dress on a new suit. You're probably more worried about if your bum looks big in it than if it's a bit loose around the back. So often these overall fit measures aren't that much use when you want to know if your bum looks big in the dress. Finally, Klein, who's written 2 excellent books on SEM, warns you, and has written a huge great chapter on this called How to Fool Yourself with SEM. I advise you to definitely look at that because it's a very useful chapter warning about many of the pitfalls of SEM. Hope you enjoyed these videos so far. I'll get around to doing some more in the next few weeks. Bye.